Hi. Today we're going to talk about a statistical procedure known as the analysis of variance. Let's get into it. The analysis of variance, abbreviated ANOVA for analysis of variance, tests the hypothesis that several means are the same. What ANOVA does not do is it does not test variances. It does not test variations. It's a misnomer. It should be named the analysis of means, but it's called the analysis of variance. It uses variances or variations to test the means. So don't get confused by the name. We are testing means. The null hypothesis is that the means are the same. And we're going to use variations in order to test this hypothesis, and hence the name, the analysis of variance. What it really asks is the question, are the means significantly different? Remember that a null hypothesis is not rejected unless we have sufficient evidence against it. Well, we say, are the means significantly different? If they're really different, then we'll say the means are not alike. But if they're just a little bit different and really can't tell that the difference wasn't caused by experimental error, then we can't. See, we say, could the difference be explained by experimental error, by just natural fluctuations in what's going on? Natural fluctuations will cause the means to differ, but that doesn't mean they're different, unless they are significantly different, in which case we'll say, hey, these means really can't be the same, they're not explained, the difference is too big for experimental error. Okay, now I'm going to give an example. Let me say in advance, this example has made-up data. This is not real data. And I do not want to offend anyone with this example, but it's an example which people remember, so I use it. And the story is this, that I went around I wanted to see if sororities on the tech campus were snobby. So I went around to 3 sororities and I measured their nose lengths, the lengths of the noses of the girls in the sororities. And here's my data. Okay, here's my data. And the first sorority, I measured a 5.5, a 3, and a 1. By the way, this had better be centimeters. I'd hate to think that I measured someone's nose at 8.1 inches. So let's say we're talking about centimeters here. And I have these centimeters, and their average is 3.25. And then in the second sorority, I got 1.8, 4.6, 5.8. Average was 4.07. Third sorority, I got an 8.1, 2.3, 5.2. The average was 5.20. Are these numbers different? Now, that's a loaded question because clearly the numbers are different. They're always going to be different. Even if I went to one sorority and I took 9 girls at random and just grouped them this way, I would get 3 different numbers. The numbers would not be the same, even though the mean that they're measuring would be the same. These things are measuring the mean length of the noses in this sorority. This is measuring the mean of the noses in this sorority, and this is measuring the mean of the noses in this sorority, and even if those means were the same, these 3 numbers would not be the same. The big question is, are they different because the means themselves are different, and these are reflecting the difference in the means, or are they different because of natural fluctuation in the measurements, natural variation in the nose lengths? Well, the way to do it is to look at what we call the variation or the variance in what's going on. Let's look at these numbers. I got a 5.5 and a 1.2. I could have, instead of getting this person, I could have gotten another one with this size nose. Evidently there are noses in this sorority around 1.2 and around 5.5. Well, if I got another one, instead of 5.5, I got another 1.2. This number would be much smaller than 3.25. On the other hand, if instead of getting the 1.2, I got another 5.5, this number would be much, much higher than the 3.25, maybe as high as 5. Let's look at this sorority. If instead of 1.8, I got another 5-something, this would be 5-something. And if instead of the 5, I got another low number, this could be as low as 3. Let's look at this one. I got an 8.1. What if instead of an 8.1, I got a 1 point something? Well, this number would be in the low 3s. And instead of a 2.3, what if I got another 8? Well, this number would be very, very high. These numbers are not typical of these numbers. This is not really a typical number. This is just the average of a wide range of numbers. The variation within the sorority is very large. This is not that typical. In fact, if this number were moved over here, or this number were moved over here, or this number were moved over here, you'd be pretty hard-pressed to catch it without actually doing the addition. Because these three numbers are typical of any of these groups, because it's clear that 3 is somewhere in the middle of this group, and 4 is somewhere in the middle, and 5 is somewhere in the middle of that. And so there's really not, these are not representative. And what we say here is that the within the group, these are called groups of data. Within the groups, the variation is large compared to the variation between the groups. And what we do in analysis of variance is we compare the within the group variations, how big they are, with the between the group variations, sometimes called the among group variations, sometimes called the group variations, but we're talking about the variability between these numbers as compared to variability within the groups. Clearly, the variability within the groups swallows up the variability between the groups. And we say that the numbers are not significantly different. Okay, what we've shown is that tech does not have snobby sororities, at least as far as nose length is concerned. And the way we did it was to look at the variation within the groups and the variation between the groups. And the variation within the groups was large compared to the variation between the groups, and therefore explained why the groups differed. The means of the groups differed because the natural variation inherent in the whole thing was just showing up there. Okay, now I went to UVA and did the same thing. Went to 3 sororities, measured the nose lengths, and here's my data. And I got 3.0, 3.1, 3.6, average was 3.25. This sorority I got 4.0, 4.2, 4.0, average 4.07. This sorority I got 5.0, 5.4, 5.2, average. These means are the exact same numbers that we had for the tech sororities. And someone's going to say, oh, but we already know that these numbers are not significantly different. And I say, wait, hold on. The reason they were not significantly different was because the difference between them was small compared to the variation within the groups. Let's look now at the variation within the group. This sorority has noses between 3 and 3.6. 3.25 is rather typical of those. If someone said, put a 5.2 here, you'd say, wait a minute, there's no way 5.2 could be the average of these numbers. It's clear that the average of these numbers is somewhere in the 3 range, and this is typical of it. Same here. The average of these numbers has to be in the 4, low 4. 5 would not do, 3 would not do. This is clearly typical of what's in that sorority. Same here. This is typical of what's in that sorority. The variation within the sororities, within the groups, is very small compared to the variation between the groups. Clearly, if this were the average, the mean nose length of a sorority, it would not be the mean nose length of this sorority. This sorority would be smaller, and this would even be smaller. So, for them, we say they are significantly different. These are significantly different, and when we have significantly difference, we can reject. What are we rejecting? We're rejecting the null hypothesis that all the groups are equal. Okay? So what have we done? We've asked the question, is the variation between the group means explained by the natural variation as seen within each group? That's ANOVA. The ANOVA null hypothesis is that all means are equal. By the way, if that's the null hypothesis, what's the alternative hypothesis, the opposite of this? Some people say, oh, all means are different, and that's not true. Not all means are equal, or not all the means are the same. Not all the means are equal is the opposite of this. If we had 3 groups and 2 were absolutely equal and the other was different, this null hypothesis would not be true. They do not have to all be different. One of them has to be different than one other, and that would be sufficient. But at any rate, the null hypothesis is that they're all equal, and we've shown that they're not equal. They're definitely not equal, and we reject the null hypothesis for this example. Okay, we've got that now. We now know analysis of variance. It's as simple as that. You set up groups, and you want to know are the means the same within each group? Well, look at the variation within each group, and then look at the variation between the groups. If the variation between the groups is no bigger than the variation within the groups, there's no evidence whatsoever that there's a difference. If, on the other hand, looking at the variation within the group, it's small compared to the variation between the groups, then clearly the groups are different, and the analysis of variance would reject. Of course, we want to do the thing just right and know at what level we're rejecting and so on. We'll do that in a minute. We're not going to be able to do it by hand. We'll bring in the computer to do something like that. However, there's another topic that I want to bring in during this lecture, which is very much related to it, and that's the topic of confounding. I was thinking of giving a whole topic of confounding, a whole lecture, but it wasn't big enough, so I put it in this one, confounding. Now, when something other than what is being tested can cause significance, that is, cause rejection, that's when you have confounding. When something other than that's being tested can cause the significance, in other words, you cannot tell that what you're testing is really doing what you say it's doing. It's rejecting the null hypothesis. Something else is rejecting the null hypothesis. If that can happen, then that other effect is confounded. The effects that you're working with are confounded, and you can't really tell which one did the rejection. And I have a simple example of that. Make life easy on us. Here's another example. I don't mean to offend anyone, but I like to give examples that people remember. Let's say I want to prove that blondes have more fun. So I make a survey. I go out and I survey 20 blondes, 20 brunettes. And every one of the 20 blondes say they had more fun. And every one of the brunettes said, no, I didn't have as much fun. Okay? Now, looking at that data, it's clear to us that blondes have more fun. They all agree they have more fun. All the brunettes say they don't have more fun. That is, the brunettes don't have as much fun. And therefore, our conclusion would be that blondes have more fun. However, what if when I did this experiment and I asked 20 blondes and 20 brunettes, it turned out that all the blondes were females and all the brunettes were males? Someone else can come along and say, well, that really says that females have more fun than males, because you asked 20 females and they said they had more fun. Asked 20 males, they had less fun. Females have more fun. Well, how can you tell whether females or blondes are having more fun? There's no way to distinguish between those properties. Those properties are so intertwined, we call them confounded. They're confounded. I cannot be proving that blondes have more fun. I cannot be proving that females have more fun. Maybe it's blondes, not females, that have more fun. Maybe it's females, not blondes, that have more fun. I don't know. I can't even tell whether it's blonde females. I can say blonde females have more fun than dark-haired males, but that's about all I can say, but that's not really what I wanted to say. So we have confounded the effects. You confound effects when you cannot separate them and decide which one is causing what you say it's causing. All right? We have to avoid that. When you do hypothesis testing, all I can tell you about that is avoid it at all costs. And unfortunately, when you see things in the newspapers, they don't avoid it. There are other things, and the way to disprove someone's published work is to go through their research and see, hey, what have you confounded? What else could have caused the effects you're proposing? They say if you eat oat bran, you won't have a heart attack. Well, I always wondered, the people that they were giving the oat bran to, they volunteered for that? Weren't they conscious of their heart? They're worried about it, so they must have done other things like exercise and not eat fat and lots of other things besides eating the oat bran in this experiment. I mean, they're in the experiment. They're conscious of the fact that, hey, you got to be careful of your heart. So I wonder, is it just the oat bran which keeps you from getting a heart attack, or is it an overall thing where you're doing lots of things? So be very careful when you read these results in newspapers. They don't always tell the whole story. Okay, let's get back to the analysis of variance and its details. What I want to talk about now is how to actually do it. Now, I'm not going to show you how to do it by hand. It's far too hard. You won't be doing this for homework. In homework, you'll just look at the data and see whether it is or it isn't. But sometimes there's a close call, and so you have to put it in. I'm using Minitab again, the computer package. In C1, I put the data, and in C2, I put which group it belonged to. So I really have here 4 groups. these 3 in one group, these 4 in another group, these 4 in another group, these 3rd in another group, and here is my data in group 1, here's my data in group 2, here's my data for group 3, here's my data for group 4, and the way you put it in the computer is you write it all into a column, and in the next column you tell which group it belonged to. So that's the input to the program, and you press a button, you say Minitab, do, and Minitab does. What you do is you say ANOVA, C1 equals C2. Just do an ANOVA on this data. And it gives a bunch of output. Programs are all alike, and yet they all say a little bit different. When it says C2, that's the groups. That's the between groups, Remember we said between groups? That's the between groups. What it calls the error, we call the within. Okay? So this is the within variation on this line, and this is the between group variation on this line. The degrees of freedom, we talked about that once before. That's the bits of information associated with each of this. There are, in this case, there are 4 groups. See? There are what? Well, there were 4 groups, so n-1 was 3. There were 3 bits of information for groups, and then there's 10 bits of information for the error, for the within. And what we're really interested in is these numbers here. This represents the variation. The mean square for error represents the variation within. The mean square for groups represents the variation between the groups. And as you can see, this group variation, the variability in the groups, is 2.8 times as large as the variability within the group. Well, is that big enough to reject the hypothesis that they're equal? I mean, it's 2.8. See, the variability within the group is just so big. The variability between the group is bigger than that. A little bit, almost 3 times as big. Is that enough for us to reject the hypothesis? Well, what the computer program does, as it always does in hypothesis testing, is give us a p-value. P-value. Remember what a p-value was. If you make a test at any level bigger than the p-value, you can reject that test. But at any level smaller than the p-value, you must fail to reject. So if someone said, make a test at 10%, which is a 0.1 level test. 0.1 is bigger than 0.09, and therefore I reject. If someone said, make a 10% level test that whatever the groups that we had in our analysis, the 4 groups, were the same, you would reject the hypothesis as no. At the 10% level, I'm sure that they're not equal. That means I'm at least 90% sure that they differ, and therefore I reject the hypothesis. If someone said make a 0.05 level test or 5% level test, I notice that 5% is smaller than the p-value. Well, I can't reject if it's smaller. I can only reject if it's larger, so I must fail to reject. Okay? I fail to reject at the 5% level. It means I'm not quite 95% sure that it's wrong. And of course, if someone said make a 0.01 level test, clearly if I'm not 95% sure, I'm not 99% sure. 0.1 is smaller than 0.09, so I must fail to reject for that also. Okay? That's how we do analysis of variance. That's what analysis of variance is about, and that's how we do it. And I'm not going to expect you to be able to do it by hand, but I will expect you, being given a computer output, to look for that p-value. Some outputs call it p-value, some say p probability value. There'll always be a p associated with it, and there'll be a number there, and it'll be sort of off on the right, and there'll be a number between 0 and 1. That's the p-value for that test. And all you have to do is look at the p-value, ask yourself what level test I want to make. If the level is higher than the p-value, reject. If it's lower than the p-value, fail to reject. Okay? We're going to use analysis of variance in the very next lecture. Try and remember some of the things we learned. Okay? See you then.